How do I actually move my slides? That's the important question. Okay, so this is a joint work with 4 other people, with Martin Bürger from University of Erlangen, Matthias Erber, Daniel Mattes, and André Schlichting. Okay, so the subject of my talk today is covariance-modulated optimal transport. I guess that most of you have come across optimal transport in some shape or form. I mean, also the previous talk was about the Wasserstein distance, which is one way of measuring distance between probability distributions using the idea of optimal transport. And so here we're looking at a different type of optimal transport distance. And I will spend a little bit of time sort of explaining the setup. So this first definition of the metric itself looks pretty much like the dynamical formulation of the Wasserstein-2 distance, where you're essentially minimizing a kinetic energy along the path in probability space that is connecting 2 measures. So if I have some, this is my probability space here, let's say just on RD. And then I have some point in this space, which is mu0, and some other point, which is mu1. And now you're looking at all the possible paths of how you can connect these two. Then you're trying to find the path which actually minimizes this kinetic energy. Now, the difference here is that the way how we're measuring the kinetic energy is different. So instead of just using the usual square norm of the velocity vectors, we are now using an inner product that is weighted with the covariance matrix, where the covariance matrix is the covariance matrix of this probability distribution at that point. And then there is a condition that these optimizers, these mu t and bt, have to satisfy the continuity equation. So that's the same like in the Wasserstein-2 distance. And so for the rest of the talk, I will use this notation of m of u denoting the mean and c of u denoting the corresponding covariance matrix. And so there's something really interesting that happens here if you try to understand the geodesics or the optimizers of this. In particular, there's a kind of competition going on between a spreading effect and moving mass around. So let's say I have my distribution mu1 or mu0 that looks something like that. And then I have my distribution mu1 that looks something like that. And now as I transport from mu0 to mu1, the shape of this distribution is changing, of course, right? So let's say in the middle I have something like that at some point. I mean, it might not be that, but let's just assume it looks something like this. So this would be mu t. And if you think of this as in terms of moving particles, you can also ask, okay, each of the particles that make up this mu0, if mu1 is also made up of particles, how are the particles transported? And for the Wasserstein distance, this is very well understood now. Now, if we're weighting with this covariance, what this essentially means is, for example, if I look at this mu t and I compute the covariance at mu t, right, then for example, in this direction, the eigenvalues are a lot larger than in this direction, right? So now if I compute my kinetic energy by weighting by the inverse of the covariance, it means that transport in directions where the covariance is large is actually a lot cheaper, right? So if I want to transport mass in this direction now, then this would be very cheap. Whereas if I wanted to transport mass in this direction, it would be more expensive. And so you see that sometimes you can actually gain something by moving mass additionally in some sense. So you're spreading out your measure along the path to decrease your kinetic energy. But if you do that, of course, you're moving mass out and then you're moving it back in. And so you have to still pay something for moving that mass. And that's how this trade-off happens. And that can generate some interesting dynamics, which we still don't fully understand. And the way how we came to defining this new metric is from a specific application that I will tell you about in a moment, and in particular, the gradient flow with respect to that metric as a PDE. So I will be talking a little bit about the gradient flow formulation for that metric. So here's the whole talk in one slide, but don't worry, I will talk more about each of these points later on. So this gradient flow, the specific gradient flow that we're interested in, is this PDE that I have up there. So if you remove the covariance matrix, oh, there's missing something. This should be dt rho is equal to divergence of rho, and then the covariance matrix, and then the gradient of log rho plus f. I have been writing this a little bit too quickly. Okay, anyways, that's what should be written there. And this is a non-local and non-linear Fokker-Planck equation because you have this covariance in there, right? The covariance is a non-local, has a non-local dependence on your density rho because it integrates over everything. And this specific PDE arises in the mean field limit of an interacting particle system that is at the heart of certain types of algorithms for solving Bayesian inverse problems. So now I'm not expecting that you're sort of experts on inverse problems, but I will spend some slides sort of telling you what that problem is and where that formulation comes from. But the whole idea of these type of algorithms is that you want to be able to generate approximate samples from some target distribution. So that target distribution, you can just write it as e to the minus f, and then you have some normalization constant. And so this function f is then the one that appears in the PDE up there. Okay, and so what I was already mentioning is that then this PDE on the top, well, which is this PDE, is a gradient flow with respect to this covariance-modulated optimal transport distance. And that gives us some tools to actually say things like, what are the rates of convergence? What are the properties of the solutions? And the reason why this is interesting at all, or why people came to formulating these types of interacting particle systems, is because having this covariance there is expected to improve the convergence behaviors. And I think now we understand much better why that is, in terms of actually understanding what are the geometric properties also of this distance, and how does it change the convexity properties of functional, if you look at it in that topology. Okay, so this is sort of the trailer of what I'm planning to share with you. Okay, so let me start with this Bayesian inverse problem. Completely different. Oh, you can't see the bottom of it. Maybe I should move the. There you go. Okay, so this is what I wrote up there is a very general family of inverse problems. And here you have some parameter space, here just RD, and you want to, should be okay. Well, I don't need that anymore, really. So you have some parameter space. This could be finite dimensional or infinite dimensional. Here I wrote it in a finite dimensional way. I mean, even if you have functions, you can usually discretize them. And then you have this forward map G that maps to some observation space. In this observation space, you can actually take measurements. So these Y's are some measurements that you actually took or some data points that somebody gave you. But these might be corrupted by some noise. And so the simplest assumption that you can make is that this noise is Gaussian distributed. Right? Okay, you can argue that sometimes that's not realistic and so on. But for now, let's make that assumption. So one thing you could picture here as or something that I like to picture, because that's how I got into these inverse problems, is climate forecasting models, for example. So if you have a climate model, you usually have many different coupled PDEs. And then there's many different things that go into these PDEs, like you have different diffusion coefficient, you have different maybe permittivity, you have maybe different boundary conditions, different initial conditions. And given all of these things, you can then plug this into this huge numerical solver, and then it spits you out some answer of like, okay, the temperature is probably this in 10 days or something, right? But often you don't know what these initial conditions are, or what these boundary conditions are, or you're missing a diffusion coefficient. So this would be your x. So basically, if you give me this x, which is your diffusion coefficient, you then plug that into your PDE, you run your whole solver, and then you get an answer. And that answer is something you can then compare with, okay, what is the actual temperature, right? Or what's the actual pressure? Now, this is why we would like to think of this forward map G as sort of a black box. Because if you think of like several coupled PDEs that you're now solving with some numerical solver, it's not even clear sort of how do you differentiate that, right, in terms of now the dependence of the parameters. So we would like to have algorithms that are both derivative free, and yeah, where I don't need to make use of the gradient of this forward map. Okay, if I have an inverse problem like that, then what you would like to do typically are two different things. So either you would like to do parameter estimation, which is basically saying, here's some observations, so I give you some y's. Now, what is the most likely x? Like, what is the most likely parameter that has given rise to these observations? That would be parameter estimation. And that is an optimization problem. So what you want to do in that case is you want to find this x star. Oh, there's also something missing. This should be argmin, which is the minimum. No, it's the maximum of the pi, which is the minimum of the f. So let me write this so that it's not argmax of pi of f. And why? Because if the pi of x is basically proportional to this e to the minus f, where f is given by this function here, then what this is asking for is the maximum of the posterior distribution connected to this inverse problem. So what this is saying is that if I have some prior knowledge of how my parameters are distributed, so let's say they're Gaussian distributed with mean m and covariance sigma, then I can write down the prior distribution. The prior distribution would just be the Gaussian. And then I have a likelihood that takes into account the model, so how the parameters gave rise to the observations. And then by Bayes' theorem, you have prior times likelihood gives you the posterior, and that would be exactly this e to the minus f. And so you will say, well, you're actually done because you can write down what your posterior is, and now you just want to maximize it. But the point is that this g of x, this forward map, is not known explicitly, right? You can query it in the sense that if it's a black box, you can stick in an x and you get out an f of x. But you don't understand really the landscape of this, right? If you try to picture sort of how does the posterior look like, it's very difficult. You cannot really do that. So one goal is to just maximize the posterior distribution, so find the most likely parameter, which corresponds to minimizing this f. Another question that people often try to answer is, okay, you don't want to just know what the most likely parameter is, but you also want to understand the distribution of parameters. So basically you want to answer, here's a parameter. Given the data you observed, how likely is it that this parameter gave rise to that data? Right? You really want to understand the distribution, the posterior distribution. And in that case, you want to sample from this pi. And that's also a very general problem, right? I give you some measure, and now you want to sample from that measure. Can you do that? So a lot of these algorithms, both for optimization and for sampling, they make use of the gradient of that function. And so here we want to derive some derivative-free algorithms. And there's a whole family of algorithms that does that. And these are called ensemble common methods. And the idea there is that you have, you start with, so let's say you have something very difficult you want to sample from, like your pi here, your target pi. So instead of sampling from there directly, what you do is you sample from something easy, like a Gaussian. We know how to sample from Gaussians very efficiently. You take that as your initial conditions for a particle model, then you set up a particle evolution, and you set it up in a smart way so that your particles evolve towards samples from what you actually want. And you might not be getting exact samples, but you might be getting approximate samples. And then you would like to prove things like, okay, how approximate are they? Like, how good are these samples that you get? And the idea is that you use ensembles of particles. So as they explore the space, so as they move around, every time they go somewhere, you evaluate this f of x at those particles. You get an understanding of how the energy landscape looks like. And you use the knowledge of all these particles that kind of communicate with each other in order to decide where they should be. I mean, where they should be in order to be more precise samples. Like that's sort of the idea of these ensemble common methods. And there is in particular an algorithm for sampling that we proposed in 2020, so this is relatively recent, that directly gives rise to the PDE that I showed you. So that's why I briefly want to introduce this, but just to say that there's a huge literature on these. And for example, this is a little twist on another algorithm that is called ensemble common inversion that can be used as an optimization algorithm. And this is a sampling algorithm. So, you know, I could give a whole talk about all these, but I don't want to do that. I just want to motivate where this gradient flow comes from. So let me just tell you a few things about this algorithm. If you just look at this first sum, so the first part of it, so forget about the last two terms, then what this is basically doing is two things. So one is that you have the g of xk minus g bar, which is the mean, right? So this is driving particles towards the mean of the g. So it's making particles collapse. And then you have the g of xj minus y. So this is driving the particle xj to actually solve the inverse problem. So if g of xj is equal to y, then already your xj is at the good place in order to solve the inverse problem. And maybe I can quickly write this down, because one, like, the easiest case is if this forward map g of x is just linear. So let's say it's just some matrix times x. And if you do that, if I just go back to the f, then this f is just a quadratic function. And so your e to the minus f is just a Gaussian. And then you want to sample from Gaussians, which we know how to do anyways. But that's not the point, right? Let's say we're starting from understanding this linear case to then be able to use this algorithm also when you have a nonlinear forward map. Yeah, so if you have this, then this first part here, so for sum over j, I can write it like this, right? X k minus x bar, which is now just the mean of the x's, the empirical mean. And then here I have a xj minus y. And if I write this in a product with some matrix on the bottom, then what I mean is always a matrix weighted in a product, just for the notation. So here now I have the gamma here, so what that means is that I can write gamma minus 1 and then a xj minus y, right? And then the next thing I can do is I can put this a on the other side, so I put an at here. Oh, I think there's missing something. Yeah, I have a lot of typos in these slides, I'm sorry. So here there should be an xk, and you're summing over k, exactly. So one thing that you can do now is you can add here minus x bar. If I do that, it doesn't actually change anything, because then I only sum over this xk, right? And then it will cancel with the mean. So I can do that. And then the next thing you can do is basically pull this vector inside and at the same time pull this one outside and write it as a tensor, right? That's just an algebra. So you have 1 over j, and then you have xk minus x bar, tensor product xk minus x bar, and then times this other vector that you have here. And this one now, you can actually think of a gradient of your function f. I mean, not the whole function f, just this first part that has the g in it, at the point xj. So what you basically get is something, so the C raw j is my empirical covariance. So you basically get something that looks like this. F, but not the whole f, just the first part of it, which is y minus g of x j squared, and then weighted with this gamma. So in other words, if you linearize your forward map, then you can write this whole first term there as a preconditioned gradient descent, right? And so this is how this covariance matrix shows up there. And now the question is, why should this be better, right? So there's a lot of literature on how preconditioning a gradient actually allows you to accelerate convergence if you precondition it with the right matrix. And so, right, the idea in some sense is that this first term is approximating gradients with differences. Because now to actually implement this algorithm, you don't ever have to calculate the derivative of g. But what you're actually doing is an approximation of this, basically. Okay, and then you have these other two terms, like the second term comes from the prior information. The sigma was the covariance of the prior information. You don't have to put this there. This is also sort of a new twist on ensemble common methods. And then you, this last part, the noise, is actually really important, because if you don't have the noise, what will happen, or even if you just put Brownian motion, or you put noise in a different way, you can also put noise on the observations, then what you will see is that these particles collapse very quickly. So if you let this run, they all collapse to a point, because this first part is driving the particles together. But if you put enough noise, then you prevent the particles from collapsing. And so then what you get in the limit is that they actually approximate something that has positive covariance. And so the new twist to this was basically to put in front of this Brownian motion the square root of the covariance, which will then, if you look at the mean field limit of this PDE, give you exactly this gradient flow in this covariance-modulated optimal transport distance. And so, yeah, this whole connection comes then through the mean field limits. So you can write down the sort of evolution of a typical particle. And this is literally the same equation as if I would write this this is after linearizing G, right? So you have this first term, and now you just replace the empirical covariance with the covariance of the actual mean field limit density. Right? That's all you're doing in order to get this x dot equation that I wrote there. And sort of when we wrote the first paper on this algorithm, we sort of wrote down what the limiting PDE is, but we didn't do much analysis on it. And so then there was relatively quickly a follow-up paper by Ding and Li, who actually proved the mean field limit with rates and all of that. Okay, so I just repeated the equation up there, and now writing it with the covariance of the density raw. And then, so in all generality, what we're interested in is more general gradient flow, right? So the gradient flow that we get as part of this algorithm is a gradient flow in this topology with a very specific choice of energy. And the energy that gives rise to this algorithm is just the raw log raw energy plus F times rho, where F is the potential, essentially. Why do the gradients fall? No, that's okay. No, that's correct. I'm not trusting my slides anymore. There should be. If you see a typo, please tell me. Okay, but let's say that you didn't know anything about this distance, this covariance-modulated transport distance, and you just look at this PDE, and you look at this energy, and you're asking, okay, how does the energy decay along solutions of this PDE? So you can just, go and calculate the dissipation of the energy, and if you do that, you already see this structure emerge, right? Because this is just by direct calculation. This prime here on the energy is the first variation, and then you take the gradient of that. And so the corresponding metric that you want then is this one here. So this looks a little bit different from what I showed you on the first slide, right? But actually you can translate one into the other simply by defining your velocity to be the covariance matrix times the gradient of phi, right? If you do that, then you, if I just go to the next slide, I think I have it there. Yes, if you do that, then you get exactly this formulation that I showed. And just to say, okay, one of the questions we set out to answer by looking more on the geodesics on this distance and so on is just to understand how can this covariance modulation actually improve convergence rate. And so we started by just looking at the properties of this distance, first of all. And this distance actually metrizes weak convergence plus convergence of second moments. So that's like the Wasserstein distance. But not all measures with second, or probability measures with second moment bounded will have a finite distance. And then we try to understand, okay, when is it not finite? And understood a few things. So one thing is that you can never transport mass in a direction that is part of the kernel of the covariance, simply because the way how this inner product uses the covariance. So one of the conditions is that the kernel of the covariances of your starting point and your target is the same. Because if they are not, then you would have to move some mass in a direction where you cannot move any mass. That's the first thing. And then the other thing is that you also have to move mass in order to adjust the means, right? So if your mean is actually, if the difference of the two means is part of the kernel of the starting point or the end point for that matter, kernel of the covariance of the starting point or the end point, then also you cannot achieve the transport. So these are the conditions. If this is satisfied, then you have a finite distance, and then you can ask the question of the geodesics and what exactly they're doing. And then it also tells you that if you look at the span of the support of your starting point, you can never get out of that. So the support of your mu t along the way in the dynamic formulation will always be inside there. And then we even have a quantitative estimate. So this is a matrix inequality in the sense of positive semi-definite matrices. This is a statement about their eigenvalues, right? And we also have what R is, but I will not bother you with those details. Yeah. No, R is just a new parameter I put here for the first time that is hiding a whole bunch of things. But actually, it depends on the action of on the value of the action. Yes, this is true for NAT between 0 and 1 along the, and that's quite useful. I mean, a lot of the proofs later will make use of that inequality. Okay, and this is one of the key insights now into the structure of this metric. I would say this is sort of the key theorem of this whole paper. And that's the fact that you can split this distance into two separate optimization problems. So one optimization problem which only looks at the evolution of the shape, and then another one which only looks at the evolution of the moments. And you can study these separately. So let me explain the notation here. The first problem is a constraint optimization problem. So if you look at what I wrote there, it's basically exactly the same thing, except that now I'm requiring that along the path, the mean is always 0, and along the path, the covariance is always identity. That's why you don't see any weights in the kinetic distance, because the covariance is always identity anyway, so it doesn't appear. And of course, this only makes sense if the new 0 and the new 1 have mean 0 and covariance identity, right? So you work in that constraint manifold. So this is the evolution of the shape. So you're basically saying, okay, we fix the mean and the covariance. We don't care about the moments. I only want to understand the shape. And then you have the moment interpolation problem, where now you have a functional that you're minimizing, which is only, so this MT and CT is a mean and a covariance that is a function of time between 0 and 1, and you're just simply minimizing over all possible functions that, okay, I didn't put in any of these inf here the condition that you have to match, of course, your starting point and the target, right? And then, of course, there's a relation between the two. And in particular, if you take an optimal curve for the actual distance, the W-cov, and you normalize it, so you shift it so that the mean is 0, and then you multiply it with a matrix so that it will be covariance identity, then that is actually an optimizer for this constraint optimization problem, right? So what I wrote down here, you could do that actually for many different choices of A. So A is the sort of square root of your covariance. And if I define a mu bar this way, then this is a normalization in the sense that it will have mean 0 and covariance identity. But there's actually several different square roots I could take of a matrix. And it will always give you something that has covariance identity. So in principle, this works for any kind of normalization that you then plug as nu 0 and nu 1 into the constraint problem. But later on, you will see that we want a specific normalization. And that is for a square root that is solving this matrix ODE. And it will become later, will become clear why we want that ODE and not a different one. Maybe just to note here that if you have an AT that solves this, then for all times you will also always have that AT transpose is equal to CT. I mean, otherwise it wouldn't be a square root, right? And also, I mean, this is always symmetric, but the AT itself might not be a symmetric matrix. And something solving this ODE will actually be non-symmetric, usually. So that's the interesting thing. We're taking a non-symmetric square root. Okay, so I will not sort of give you the whole proof, but I just want to give you an idea as to where this splitting comes from, how you get that splitting. And the idea is that you rewrite the optimization problem. So you first look at this WMC. This is basically the same problem as the original metric, with the only difference that now you're fixing the mean and the covariance, but not to 0 and identity, you fix it to something given. So I give you some mean and covariance, which is just a function of time, where time goes between 0 and 1. I give you that. And then given those M and C, you are solving this optimization problem under the condition that your mean and covariance always follow that given function. So once you have an optimizer to that, you then go and you optimize over all possible choices of MT and CT, right? And that gives you the same thing. I mean, that's just a different way of rewriting the same optimization problem. But this is what allows you to do this splitting, because now you can go and actually normalize your optimizers to this WMC, and you will see that the kinetic energy nicely splits into these two parts, where the second part only depends on the moments, and this first part, I didn't write down what Vt is here, but Vt is basically a function of your A and your M and your mu, and this is then the usual kinetic energy. And the mu bar is a normalized density. And it's the normalization with the specific choice of A. So this is where this connection comes from. Okay. Let's see, I'm going much slower than what I thought. So that's why I only put very few slides. Okay, so then the next thing we try to understand is how do the optimizers look like? Like how do the geodesics look like, both for the moments and for the shape? And can we prove that they exist, first of all? I mean, that's always the question that you start with, right? And for the moments, that's actually quite a doable problem. For the shape part, it's more complicated than what we thought. So this is now for the moments. So for the moments, you can show that an optimal interpolation always exists. So that's good news. And then for some special cases, you can find explicit solutions that you can write down. So if you have that the means are the same, for example, then you can write down the optimal covariance explicitly. And maybe to give you some intuition here also, so if your starting covariance and your end covariance commute, then this formula that you see up there simplifies. And what do you get then? You get simply C0, 1 minus T, T1, T, right? Yeah, I think that should be correct. And so you see that it's really just an interpolation, right? And if, on the other hand, your covariances are the same, but the means are different, then you can ask, okay, what's the eigen decomposition of your covariance matrices? And you can write that in this way, where the lambdas are the eigenvalues and the e's are the eigenvectors. And then you get an explicit expression for the moment optimization problem in terms of the distance of the means and the, that should be the norm of delta, I guess, because these are still vectors. So this is the norm of delta divided by 2 times the eigenvalue. And for Gaussians, things are even, so really the moment part is in some sense the Gaussian part, right? Because if I look at the distance between Gaussians, then this is fully captured by just the mean and the covariance, and so then the constraint part will be 0. If I look at the distance between Gaussians, the shape part will be 0, and you only remain with the moment part. And there's a few more formulas that we derived for that, but maybe just as an interesting sort of comparison to Wasserstein 2, if you have the Wasserstein 2 distance between 2 Gaussians that have different means but the same covariance, and now you make the distance between the means larger, so you let this delta go to infinity, the way that this Wasserstein 2 behaves is just linearly in this mod delta. Whereas for this covariance-weighted distance, it's a logarithm of the delta. So fundamentally different. Okay, and next, what about the shape part? Okay, what about the shape part? It turns out that this is actually quite difficult, as I said, and we still haven't fully solved it. But so before we talk about the covariance-modulated constrained shape part, let's talk about an easier problem, which is a variance-modulated optimal transport. And what I mean by that is now instead of just weighting the inner product with the inverse of the covariance, you're weighting the inner product by 1 over the variance. And this is much easier because now you're having a scalar, not a matrix, right? And you can have the same splitting into a constraint distance, which is the shape part, and then the moments, where now instead of the covariance, you look at the variance of your densities. And if I look at this variance constraint optimal transport, so this W01, this is something that has been studied before. So there's a very nice paper by Khaled and Gangbo already from 2003 who looked at this in a different context. I think they took inspiration from kinetic theory, because you can think about this as basically rescaling time with the variance in a kinetic equation. I mean, if you look at the corresponding PDE. And there's a very nice connection that they observed between the geodesics of this problem and the geodesics of the Wasserstein distance. So essentially what they observed is that if you take your mu0 and your nu0 and nu1, you could also compute the Wasserstein geodesics between them. So if you have the Wasserstein geodesic, which you know exists, then you can renormalize it. So you shift the mean to 0 and you normalize the variance to be 1. And that actually gives you an optimizer for this distance, just after reparametrizing with time. So there's another step you have to do, but and this way they answered this question of existence of geodesics, because you use the fact that you know that Wasserstein 2 geodesics exist. Unfortunately, this is not true for the covariance-modulated distance. And in fact, we constructed some examples where clearly the rescaled and renormalized Wasserstein geodesics are not the best, are not optimal for the covariance-modulated one. Okay, so that's what I just said up there, the first point. So the existence of optimizers for this shape part is essentially still open, but we were able to prove that optimizers exist if you have this condition that mu0 and mu1 are close enough. And I think that's basically just out of the way how we prove this. So I hope that it's actually true for any mu0 and mu1, but who knows? I mean, there could be some funny things that are happening that we haven't understood yet. And then I could also talk about convexity, but I think I will not do that, given the time. Just maybe as a summary, if you look at the raw log raw energy in the constraint metrics, that is actually one convex. Whereas in the Wasserstein 2 metric, it's just greater or equal to 0. I mean, you don't get any convergence rate from that. So in the constraint metric, you get improved convexity property of the key function you're actually interested in. So that explains also why you get improved convergence rate. And then the quadratic potential, which usually is what gives you the rates, right? If you have a Fokker-Planck equation with some quadratic potential, then the lower bound on the Hessian of that potential is what gives you the rate of convergence. But here, that's not the case, because this is just constant. That's interesting, because your convexity comes from a different term than it does in the Wasserstein, and therefore is independent of the potential. And you can see that very nicely if you look at Gaussian targets. So if you look at f's that are just quadratic, B here is the covariance matrix of the target, and x0 is the mean of the target. And then you can actually write down the moment equations. You can solve them explicitly. I only wrote it here for the covariance, but then you can get explicit sharp convergence rates both for the mean and for the covariance. That's very nice. The rest I think I already said. But yeah, so what we also looked at in order to understand these convexity properties is evolution variational inequalities. Because these EVIs are another way of characterizing the gradient flow. So if you have an EVI for a specific distance, for a specific energy, then that is another way of saying that these mu t's are solutions to the gradient flow that distance with respect to that energy. And so we were able to prove that for the constraint metric, so just for the shape part, and for the moment part, we were struggling a lot, but we were able to also get some EVI under some conditions, which I will not go into now. But once you have this EVI, you can also get convergence rates, exponential convergence rates. And so what's really interesting here is that these convergence rates are independent of the potential, right? They're independent of B. So if you would do this in the usual Wasserstein 2 distance, if you had a Fokker-Planck equation that is driven by potential, then the convergence rate would be given via this potential, right? And for this type of PDE, the convergence rate had been investigated by this paper by Carrier and Bayes last year. And they looked at the convergence in Wasserstein distance for the same PDE, so the same gradient flow. And they got the same rates, but they had a huge constant in front. And that huge constant comes from the fact that they were using the Wasserstein 2 distance for something that is really in this covariance-weighted topology. Okay. And then there's also splitting of the energy in terms of the shape part and the moment part. And you can derive separate convergence rates for the shape part and the moment part for the energy. But I think I will, this is the last slide. So the difference between the variance and the covariance modulated gradient flow is basically that for the variance modulated, the potential B shows up in the exponential rate, whereas for the covariance weighted one, it shows up as a prefactor. And of course, in terms of convergence, that's very nice. I mean, that's why it's actually sort of worth looking into this topology, in my opinion. Okay, and so just to wrap up, the way how we came to this metric problem is from these Ensemble common methods for solving Bayesian inverse problems. And then when we looked deeper into this metric, we realized that you can split it into shape and moments, and then looked at these problems separately. We have local existence of geodesics, not global ones yet. We have some improved convexity properties and some better understanding now about these universal convergence rates for quadratic potential. But yes, as I said, there are still many open problems, and I will stop here. Thanks a lot.
So we have time for questions. Go ahead.
So one thing I was wondering about is, so the picture you drew about how you can use large covariance to get faster, smaller distances, it's kind of reminiscent of the picture of the behavior of a W2 geodesics on curved manifolds. In that, if you, so one of the outcomes of the study of gradient flows on manifolds is that curvature only helps you. Now, if I look at an interpolating curve between, let's say, two Dirac masses at endpoints on the sphere, then the interpolation kind of halfway through, the support of the interpolation gets bigger, and then it goes back down. So somehow in positive curvature, one of this is kind of characterized by when Minkowski inequality is one of the markers of positive curvature is the support of the interpolation should be bigger than the endpoints in a Wasserstein space. Mm-hmm. Is there something to do with
yes, but to really understand how these things are connected is exactly what we are trying to picture to make that precise. So I mean, what you were just saying is absolutely right. What you can, let's say, if you think of the distance between two Diracs, and let's say you picture these Diracs as lying on a ball, where this is sort of telling you where the Dirac sits. So you have maybe one Dirac here, Dirac x0, and then you have another Dirac here, Dirac x1, right? then the Wasserstein geodesic between them would be basically this line. And if you look at the constraint distance, you have to always have variance. You always have to be on this sphere. So you have to go up there. And so what we were thinking is that, oh, maybe you can translate this one into the Wasserstein geodesic. But no, you cannot. So there's still something we haven't quite understood. And I think it's related to rotations. Because if you have this covariance matrix there, you can rotate things along the geodesic as well. But yeah, this is just intuition. There was a hand there, and then there was another one.
So if I understand correctly about the variance constrained versus the covariance constrained problem, do you have examples of two measures with identity covariance, or I guess it would be identity variance, and mean zero, so that when you transport along the variant, when you solve the variance constrained problem, the mean becomes non-zero in between? Does that happen?
The constraint problem always means that you have to remain also mean zero.
Oh, the variance constraint also has the mean zero.
Yes. So
okay,
I'm not sure if I get you correctly. So there's the variance constraint distance, where you're constraining the mean to be 0 and the variance to be 1. And then there's the variance modulated distance, where you don't have any constraint on the means, but you weight your inner product with 1 over the variance.
No, I think I just misunderstood the variance constraint problem.
Yeah, they're all mean constrained as well.
Okay.
I just didn't put that into the name. Yeah.